All right. See, so you don't understand the question. Okay. So you, by the way, what are some electrical components that you know about?
So you mean like what, circuit, voltage, resistance, power? I mean things like that.
Well, the components are a little bit of a physical thing, right? So give it a try again.
Or you mean like a conductor, the controller, uh, the energy source, things like that.
Okay. Yeah, basically. Um, there are certain things you must understand as it pertains to electrical components. Electrical components, um, all of them behave differently when it comes on to when current and voltage is applied to it, right? They have their own way of operating. A resistor operates different from a capacitor. Have you ever heard about a capacitor before?
Yes, sir.
What is the purpose of a capacitor?
Sir, it stores and releases energy into a circuit.
Exactly. Um, what about a resistor?
So doesn't the resistor regulate the amount of energy in the circuit?
Okay. Yeah, I mean, you're not incorrect about that. Um, but as the name suggests, resistor, right, which links to resistance. So basically, a resistor is a simple device that will resist the flow of electricity, right, or would resist the flow of charge for the most part. As you say, it regulates certain things in the circuit, so we can work with that. All right. Now, a resistor has its own IV curve or IV character. When you say IV characteristics, characteristics has to do with how the thing operates. So let me show you now. So a typical um, IV IV curve for a resistor or IV characteristic graph for a resistor would look like this, right? What this is showing us is that as my voltage increases, my current increases, right? For this is for a typical resistor, right? That's how it behaves. There are other components such as a lamp, a filament lamp. For the IV graph for a filament lamp, that would look something like this, right? So it does not have a linear shape to it, right? At some point, uh, with an increase in voltage, no more current will be able to can, well, not say no more, but the current is going to remain constant at some point, right? So we're seeing here that the also the resistance is going to be at a constant value at some point, right? Meaning that resistance is not going to change. So different components have uh, a different graph in itself. There's another component what we call um, a diode. You ever heard about a diode before?
Yes, sir.
You know what the purpose of the diode?
It's like a type of switch.
All right, fair enough. Yeah. When it comes on to the diode, right, semiconductor diode, right, the shape of that now looks something of this nature, right? Right. And you could also have an additional part of the graph to it. But the main part is this part. right? It just shows you how the thing works. So this in itself shows us that with an increase in voltage up to a point, no current was flowing. But when you increase the voltage further, right, you realize that the current now starts to flow. And this basically explains how the thing works. And as you said, works as a switch, right? So maybe if the voltage is not at the amount that it needs, then no current is going to flow through it, right? But this is a lot of information, but you definitely need to go back over it to know which graph corresponds to which component. All right. You get me so far, sir?
Yes, sir.
All right. So we need to answer the question. It says that with the aid of a clearly labeled circuit diagram, it says explain how the IV characteristics of an unknown electrical component may be determined. Now, for this now, I'm going to go ahead and draw the circuit, right? So if you have a component, Zane, and you want to know how the component is behaving, you could build a simple circuit. And obviously, if you want to find the IV characteristics, then you would obviously need to measure the current flowing through it, flowing through that what you call it now, that electrical component, and you would obviously need to know the voltage that is also flowing across it as well. So all I'm going to do here is to just set up a circuit, right? Now in my circuit, I need an ammeter, right? By the way, what this thing here is what we call a variable resistor. And then now, this is where my unknown component comes into play. I don't know the component. I'm just gonna just give it a symbol. I shouldn't even give it a symbol, right? But uh, let's just give it and just put X beside it, right? Because this can be problematic if I use this symbol, because this symbol is a symbol for a resistor. But then now the final thing that I'm gonna do is to include a voltmeter right here, which is technically measuring the voltage across this uh, unknown component. I could have drawn it differently. And let me show you the correction that I could have done to this. I could have simply put the voltmeter across here, right? So that would be basically the setup of the circuit. And as you can imagine, this is going to be your power source, your battery, right? You have your negative terminal, your positive terminal. This is your ammeter, right? This is the unknown component. This is your voltmeter. And that is your variable resistor. I mean, chances are you might not see another question like this in your life, related to, the exams and so forth. But at the end of the day, we're just doing past paper questions, and I guess this can kind of just shed some light to us. Now, what we're going to do in this circuit, because if I want to find the current flowing through my unknown component, it means that I need to vary the current. And one way I can vary the current is by altering the variable resistor. So if I change the resistance of that variable resistor, then chances are it's going to affect the current that is flowing through the unknown component. And if the current is changing through the unknown component, chances are the voltage across that unknown component is going to also change. So by just constantly varying the voltage using the variable resistor, At some point, I'll be able to can get enough values to essentially plot a IV graph, plot a IV graph, and basically plot the graph and show what the thing is really talking about, what kind of component it is, if you see what I mean. If you have any questions, feel free to ask.
No, sir, no questions.
All right. And then now you just explain it basically. So as I would have just explained a while ago to say that you just vary the variable resistor, right? And with varying that variable resistor, the current is going to change, right? And once the current changes, the voltage is going to change. You just need to record those values, and then you just plot a graph, and then you might just be able to can determine whether this is a resistor or maybe a capacitor or maybe a diode, that kind of thing. All right. Okay. Now let's continue here. It says that the lights in a room are connected as shown in figure 5. It says that each battery has a resistance of 1000 ohms. Here's the circuit. It says determine the total resistance, and also it says for us to determine the current drawn from the supply if all three bulbs are lit. All right. Now it's a 6 marks question, so obviously maybe to find the total resistance, that value maybe value 3 marks, and then the other value 3 marks. Now, do you think you would be able to can find the resistance for this question?
Sir, the total resistance, we need just be adding the resistance of all three bulbs together.
Why would you do that, or why is that the only case or the only way of finding the total resistance?
Well, sir, that's the only way I remember.
All right, so you know after this lesson now you're gonna have to remember everything as it pertains to this. No, so you go. Yes.
Oh, yes, sir.
All right. So by examining this circuit, so by way of looking at the circuit, you must understand that you see, there are several types of circuits. You have a series circuit and a parallel circuit. What do you remember about a series and a parallel circuit? Let me hear what you have to say about that.
Sir, in a series circuit, the the resistors are all connected together in like one chain,
Mm-hmm.
and in a parallel circuit, the resistors, well, they don't really, I'm not explaining. The the resistance, they don't really, the resistors don't really flow along like the same path. I don't necessarily know how to explain it, sir.
All right, no problem, man. There's nothing wrong with you not being able to explain it, but I'll explain it for you, all right? Or I'll clarify. But yeah, you were correct about the series um, information. Now, I think you know when something is connected in parallel, right?
Yes, sir.
Now look at that circuit and see what resistors would you classify to be in parallel.
Or R2 and R3.
R2 and R3. All right. Now, if you have resistors in parallel, what way would we generally use to find the total resistance when you have resistors in parallel?
Uh, hmm, hmm. Sir, I don't know the formula for parallel resistors.
All right. So when you see a question like this, we have to analyze it and see what resistors are in parallel. If I have resistors in parallel, then I have to find that total resistance first. So this is what we're going to do. So because R2 and R3, they're in parallel, right? Then here's the equation. There are basically two equations mainly. And this is when we're talking about resistance in parallel. So we could say 1 upon RT is equal to 1 upon R2 plus 1 upon R3. Another way how you will see the equation is to say RT, right? And this is obviously in parallel, is equal to the product of the resistance over the sum of the resistance. So R2 times R3 divided by R2 plus R3. So easy way to remember this. Once you have two resistors in parallel, then you can use this method. So this is for only when you have two resistors in parallel. If you have three resistors, then you have to use the first formula, right? But the first formula can be tricky because you're not trying to find 1 upon RT, you're trying to find RT. So at the end of the day, you'd have to inverse the answer. So, but because we only have two resistors here that are in parallel, then we would say the product of the resistance divided by the sum. So product over sum to find the total resistance in parallel. So because R2 and R3, they have the same resistance, which is 1000 ohms, then I could say RT, right, is equal to 1000 times 1000 divided by 1000 plus 1000. So we would get 1 million in the numerator. Divide that by 2000. When we do that, we're seeing that RT in parallel is equal to, so that's going to be 500 ohms, and you have to remember the units. Following me so far?
Yes, sir.
Have any questions for me, sir?
No, sir. No questions.
All right. So we are what's the next thing you think we might possibly do in this case?
Sir, repeat that, please. What's the next thing we do?
Yeah.
We have to calculate the. Well, it says we have to calculate the current. So.
No, but we're not finished here. What we just calculated was the total resistance for in parallel. So we still don't know the total resistance in the entire circuit as yet.
Oh.
So normally, this is what we would do. Would redraw the circuit. And then now, you draw, let's just draw a resistor instead. So we're going to put a resistor right here. And this resistor that we are drawing here is going to be, it's going to have the resistance of the two resistors that were in parallel, right? So this now is 500 ohms, because we would have found the total resistance, uh, technically speaking, using the formula just now, right? So we'd have done that. So I would just include back that resistor in this circuit, and I would have already have R1, where R1 is 1,000. Follow me so far?
Yes, sir.
All right, now that I have that information, I now need to find the total resistance. What kind of circuit are we looking at right now?
Is that a series circuit?
It is a series circuit indeed. All right. How do we find the resistance in a series circuit? Would you happen to have an idea? Of how we would find that?
Sir, when you just add the resistance of both
Yeah,
of yes, sir. Just add all the different resistances.
definitely. So now the RT now, which is the final resistance, is going to be R1 plus RT in parallel. So we can now put in that information. So R1 is 1,000, and we're adding that to 500. And all of these are ohms, by the way. So we need to put in the unit for ohms. So RT at the end of the day is going to equal to 1,500 ohms. So you go.
Yes, sir.
All right, so that's our resistance. Now the question is to find the current drawn from the supply, which is the power supply, if all three bulbs were lit. Now these questions are not generally hard, you know. It's just a matter of you understanding what is happening in the circuit. All right. So obviously there's a total current in the entire circuit, and that current is coming from the power supply. Now, if I know the total voltage that is supplied to the circuit, and if I know the total resistance that is supplied to the circuit, or in the circuit rather, then I can find out the total amount of current that is being drawn from the power supply. Do you know of an equation that links these variables that we could possibly use to find out certain information or find the current? Do you?
Repeat that, sir.
Yeah. Do you know of any equation that we can use to find the current?
Sir, I equals VR.
All right. So I think your transposition might be incorrect though.
I equals V divided by R.
Exactly. Right. So we would use the equation that says I normally start off with say V is equal, R is equal to V upon I, and of course this is basically Ohm's law. So if you see a question that says Ohm's law, right, this would be Ohm's law, and R is going to be your constant basically, which is the resistance. Now if I transpose that to make I become the subject, then I is going to equal to V upon R. if I want to find the total current, I must know the total voltage, I must know the total resistance. Total voltage is what is supplied to the system, and the system gave us 110 volts. Also, we know the total resistance because we would have calculated that a while ago. So we know the total resistance in the circuit. So we can find out how much current is going to be drawn from the power supply. So I is equal to 110 volts, divide that by the total resistance, which is 1,500 ohms. And when we do the mathematics here, all right, you should be getting that the current that is drawn from the power supply is going to be 0.073 amps. Or in other words, we could say 73 milliamps. Or we could say 73 milliamps. You think you understand?
Yes, sir.
All right, perfect. Now, the question continues. It says that a micro oven, right, consumes 1,100 watts when operated at high power. It says, what is the minimum current rating for a fuse to be used to protect the oven if the main potential difference is 110 volts? By the way, what's the purpose of a fuse? Do you know the purpose of a fuse? Hmm?
Um, mm, uh, they, it's something about when there's too much current in the flow. When there's like too much current in flowing, sir. I don't really know what to say.
Okay, okay. Yeah, but what if there's too much current flowing, then why would you need the fuse? Like, what's the purpose of it? You ever hear?
Um,
Go ahead.
oh, never mind, sir. You can continue.
Alright, so you ever heard the term that a fuse blow before? Like a fuse blow or blow fumes,
Yes, sir.
right? Now, the construction of a fuse, right, is basically a piece of wire. You know, it's really just a piece of wire. Now, what happens is that if the current exceeds a certain value, what you're going to realize is that the fuse or the wire in the fuse would eventually break if too much current is flowing through it. Because current, um, is actually particles that are flowing, which is basically electrons. Now, if the wire is too small or too thin to allow those electrons to pass, then chances are it's almost like a blood vessel. You get what I mean? Like, if there's too much pressure in a blood vessel, then it will burst. Following? So it's the same thing as a fuse.
Yes, sir.
So in the electrical industry, a fuse is used as a protective device. Now, there are times when if you go into electronics, you're going to build circuits, and you might have a very expensive component in the circuit that you want to protect it against high current. It is much cheaper to to replace a fuse than to replace maybe an Arduino board or some expensive component. So what you would do is to design the circuit in such a way that you include a fuse in it, so that if too much current flows in the circuit, then the fuse acting as the safety device would break. Once the wire in the fuse break or burst, right, then it cuts the entire current from flowing inside of the circuit. And of course, that would now protect the overall components. And you just simply just need to just replace the fuse and probably fix the current issues that you might be having. You get what I mean?
Repeat that, sir.
Yeah. I'm trying to understand which part did you get? Which part did you hear me saying clearly?
No, sir. Just repeat the last part.
Yeah, so the last part I was saying is that if too much current ends up flowing into the circuit, then the wire in the fuse would break and would cut the current from flowing to the other parts of the circuit, which would safeguard against the damaging of the components, right? The simplest thing now to do is to just replace the fuse and check to see what the problem is, why the fuse would have break in the first place. Now the symbol for a fuse, as we're talking about it, is this. So this is a symbol of a fuse. That's a symbol. So inside here you have a piece of a wire. So when the current is too much, that wire is going to break, and once it breaks, no current can flow through the circuit. All right?
Yes, sir.
Perfect. Now we continue here. So we need to determine what current the fuse must be rated at, right? Because the fuse have to have a current rating. So what I mean? It must have a current rating. So in order for us to find that out, first we must understand the amount of current that is needed to operate the microwave oven. How do you think we can find out the amount of current that is needed to operate the microwave oven? What do you propose? Hmm? Do you have a proposal of how we might answer this question?
Proceed, sir.
Yes, I see, yeah.
Would it be P equals IV? Could use that formula, then transpose it for I.
Perfect, man. Perfect. Perfect. So we want to find I. I is going to equal to P divided by V.
P divided by V.
Yes, man. We know the power, which is 1,100 watts. Divide that by the voltage, which is 110 volts. When I do this mathematics, I'll get the amount of current that that is needed to operate the microwave oven. right? So these questions can be, I wouldn't say tricky. At the end of the day, the current rating that you would want, the minimum current that you would want to use to operate the fuse would be a 10 amp, um, you know, 10 amp rating type of a fuse. Now, that's um, the safest uh, value we can use here, right? We wouldn't want to use a higher value. If we use a higher value, then it means that you would possibly damage the component because the component only needs 10 amps, right? Uh, so yeah, I believe this will be the answer here. Um, it can be a little tricky thing to understand sometimes, right? Because if let's say for example, no, if the current is rated at 10 amps, right? If the volt is rated at 10 amps, then it could mean that that is the voltage, or not, no, that is the current that would basically break the fuse. But they look at it in some regard to say that current will be the safe current as well, right? So even though that current can break it, we can also classify it to be the safe current. So we're right on the border, if you understand what I mean. Let me know if you get me.
Sir, repeat that, please.
So just now we found out the current. You see, this current that we find here is related to that of the current that is required for the microwave to operate. Now, if I rate the fuse as at 10 amps, what it is really telling me is that if I am at 10 amps, if the current is at 10, then it can break, but that current is going to be a safe current, if you see what I mean. And also, what it also means is that if the current was supposed to exceed 10 amps, right? Then the volt, not the volt, but the fuse would essentially break at that point because the rating of the fuse that you're using is a 10 amp fuse, right? I hope you understand.
Yes, sir, I understand.
All right, sounds good. So we would have covered a question related to um, resistance just now. The next question here that we are going to look at is a radioactive type of a question, right? What do you remember about radioactivity and so forth? Like, what comes to mind when you talk about radioactive substance and all that? What comes to mind?
Not much, sir. Not much.
So tell me the much that comes to mind. Tell me now. You would have learned about radioactivity, right? And radioactive substance already.
I just remember doing the lab.
Okay. So in terms of the content area aspect, um, any information that you'd have remembered related to that? Tell me about the lab that you would have done. You heard me? Tell me about the lab that you would have done.
Yes, sir. Sorry about that. In the lab, we had some coins, and we had to put the coins into like a jar, and we picked heads or tails, and we'd shake the jar, and we throw out all the coins. And depending on whichever side we picked, any coins that landed on that side, we leave them, but the other coins we take them out, and we continue that process until there were no coins left.
So what was that lab? What was the essence of it, if you remember? I understand everything that you said, but I just want to break
It
down.
was to determine the half life of an I just remember it was to determine the half life of the average half life of an atom,
Basically, yeah,
something like
yeah,
that.
yeah. All right, no problem. All right. Now, one of the things that you must understand about radioactivity or radioactive decay is that in the process of a radioactive decay, right, there is what we call the splitting of the atoms, right, or the splitting of the nuclei and all of that kind of thing going on there. Are you familiar with that?
Repeat that, sir.
Yeah. So I'm saying here that in the whole process of radioactivity, right? Radioactivity on a whole is the process of disintegrating the nuclei of an atom, right? And in that process of disintegrating the nuclei of an atom, there are several things that are occurring. One, energy is being released. Two, particles are also being released. All right. And another thing is that new substances are being formed as well. That's what happens in radioactivity for the most part. If you agree, let me know. If you don't agree, then we can talk some more. Are you still there?
Yes, sir, I'm here. Understand.
All right, fair enough. Now, there are three main, um, I would say, radioactive um, source in a sense, right? That that we can talk about whenever a radioactive substance goes through the process of decaying. Now, in some substances, they will give off what we call an alpha radiation. There are some that is going to give off a beta radiation, and there's some that is going to give off a gamma radiation. All of these things here are mainly particles for the most part. Do you know what an alpha radiation is, or what's an alpha particle? Would you happen to know?
No, sir. No, sir.
All right, an alpha particle or an alpha radiation is technically a helium atom, right? And you know helium is He, right? So whenever we talk about alpha radiation, you're basically giving off a helium um, nuclei. When we talk about beta particles or beta radiation, beta radiation, as a matter of fact, for alpha, there's a symbol for alpha. I wonder why the symbol just slipped me a while ago. Yeah, I think this is a symbol. No, I forgot the symbol. Why is it that? All right, and I remember this one. For beta, the symbol would be this, right? And as I was saying, that a beta is basically an electron, right? So beta is an electron basically. And for gamma radiation, that is technically um, light. So you know they would say it's not a particle for the most part. That's what they're saying, but you know it's basically an electromagnetic radiation into light, right? It's you know it doesn't have like a a specific item like but it's just light basically, right? And the symbol for that is this thing right here. I'm trying to remember the alpha symbol. I'll show you eventually what the alpha symbol looks like. Give me a second here. I think it's this though. I think it's that symbol. Let me just check. Yeah, it's this.
Oh yes, sir. We got notes on this.
Okay, good. Yeah, man. Perfect. All right. So yeah, in the process of radioactive decay, you can give off all of these substances: alpha radiation, beta radiation, and gamma radiation. As we said, that gamma radiation is simply put light, right? Now the question is for us to it is suspected that a certain radioactive source emits alpha, beta, and gamma radiation. It says that with the aid of a clear or with the aid of a diagram, describe how the presence of any two of these three types of radiation in such sample can be confirmed. Now, there are several ways you can look at this, right? There are several ways. One way we could look at it is by way of a cloud chamber. There's a thing we call a cloud chamber, and you guys definitely have to go back over these information here, right? Just for better understanding of the core concept. So if I want to, so yeah, there are more than one ways we can actually detect or to prove that these particles exist. We could use a cloud chamber, or we could use another thing, what we call a Geiger Muller tube, right? Geiger Muller tube. So this is a counter. And then no. I'm trying to see if I'm drawing the diagram correctly. I never really have this plan in mind, and this is not what I wanted to draw in the first place. But um, let's see here. Let's imagine that this is a sample, right? And I'm going to connect my counter to my um, Geiger Muller tube. This is the Geiger Muller tube, or this we could call it a detector. I think they're better equate they're better diagrams. I'm going to see if I can just show you on the internet what it looks like mainly, because I don't think I'm really drawing that perfectly, right? So this what I'm going to show you here would be almost like a setup uh as to what right. So that thing that I was drawing a while ago would almost look something like this in a sense, to some degree, right? It's not exactly, but what I was basically doing here is to set up my detector. Now, uh, clearly, when you have the detector set up like this, the radiation and that would be given from the sample would possibly travel towards the detector. Now, based on the distance that is in between the Geiger Muller tube detector and the sample, right? Then now that can uh, tell what source is being emitted based on the fact that the counter would receive a pulse, right, to signify whether something was detected. So depending on where you put the Geiger counter, right? So if the Geiger counter was closer to the to the source. What if the Geiger counter was here, right? What if it was connected here, and you are now detecting a lot of count rates? By way of detecting a lot of count rate, it means that you're obviously detecting a radiation that travels very or travels in a very short distance mainly, right? So that would possibly be at least alpha particle, because alpha particle does not travel very far through the air, right? It probably travels at least maybe 2 centimeters in air or so. But no, let's imagine that we move now the detector further away from the source. If you move the detector further away from the source and you realize that the count rates have now decreased, then it goes to show that you're no longer detecting alpha particles, but chances are, depending on how far you're away from the sample, then you might be detecting beta particles, right? So that is kind of like how. Um, but another thing I should make mention of is the fact that sometimes they use a piece of lead as well, or some type of aluminum to put in front of the source, right? Because when you put the aluminum in front of the sample, aluminum is able to block alpha particles, right? So if you put the aluminum in front of it and you realize that you're not detecting anything, then you know that alpha is being blocked. Also, and if you're detecting a small count rate, then chances are you're probably detecting either gamma and beta, right? So it's a whole lot of things going on with this simple experiment, right? The diagram, of course, is something that we should become a little bit familiar with. Trying to see if I can find a more unified. But I want you to let me know though if you understand to some degree what we're saying here. Let me know. Let me know. Touch.
Yes, sir.
So this would be the easiest setup, you know. The easiest setup of this experiment would be something like this, right? So this is one way. There are other ways that I'm going to just ask you to just probably just revise that, right? When you're looking over the thing. So there's also another thing we call a cloud chamber. You could use a cloud chamber to identify alpha particles and so on, right? Now, to just continue the question, it says that it wants us to calculate the energy that is released in a solar fusion of barium, or that type of word. I don't know how to pronounce that word from ever since. Are represented by this basically. So this is what we call a nuclear fusion. Fusion. Nuclear fusion always takes into account lighter nuclei. So you would fuse lighter nuclei together to form a more heavier nuclei, and in that process, energy is released. So one example of nuclear fusion is how the sun creates its energy. So the sun on a whole is somewhat made based off of this type of solar fusion, or this type of nuclear fusion. Now, with recent checks, I realized that China is on the verge of making an artificial sun. So more than likely, they would obviously be they obviously would be using some type of nuclear fusion in the process. All right. Now, when it comes down to this question now, right? They want us to calculate the number of energy that is released, right? Not sure if you have ever done any question like this before. If you have, let me know.
No, sir.